If you guys want to talk to your neighbor next to you, that's fine. After you guys do that, I'll give you another one here. Let's see. Thank you.
Then the problem is like more of a
Alright, so let's talk them through. Let's do 6. So what do you guys say about what is f of 6? Right. Does not exist, undefined. Okay. So there's a vertical asymptote there. Actually, that reminds me of a good question. Okay, let me ask you guys this question. It's not really related, but can I do that? Is it possible for a function to be? So right here, I just said, oh, the function's equal to whatever, I don't know, -5, let's say. So at 6, it equals to -5, but then there's a vertical asymptote right there. Is that allowed? Is that an illegal function? Okay, so there's a difference between it's not a function like you've seen so far, but is it possible that it is still a function?
Would it be one of them? Yes.
Like what is it? What is it? What do you need to have for it to be a function? Vertical line test is usually what you use, right? Does that pass the vertical line test?
Nope.
It does, right? That is a function. Yeah. It would be what kind of a function? Piecewise, exactly. Right? It's a piecewise function, but it's already a piecewise function because look at how weird it is. It's defined differently for different parts of the graph, right? So it could be that this particular function equals to -5 at 6. The only thing preventing that from being a function is if there was some other y value, right? So like if it can't equal to -5 here, but then also equal to, say, 4. Is that okay? No, right? Because that's not a function. So, okay, all right. So what did we decide?
So you can be
that is a function, right? Yeah.
So does that mean that you can have a point on a vertical asymptote?
Exactly. That is. Yep. Totally.
How?
How? Okay. Here. Wait. Let me get another piece of board here. Let me look for more board. Oh, I don't have board, but I have a bigger eraser now, so that's okay. Look, I'll erase. Okay. I'm going to define a function. Are you ready? I'm going to write down a function. Let's see, right here. F of x equals to 1 over x let's say 2. Or sorry. What does that look like? That function right there. It's 1 over x when x is greater than 0 in absolute value, meaning when x is greater than 0 or less than 0, right? So when x is not equal to 0. So what does that look like? Well, that looks like this, right? So just your basic rational function. Like that. But then it equals to the number 2 when x equals to 0. Right there. So that's why I said it's not a function that you have seen so far. It's a little bit on the weird side. But in calculus, we have a lot of weird functions, you know, kind of along those same lines. So, yes?
I thought the whole point of an asymptote was that, now I'm confused, that I maybe don't know what an asymptote is.
Well, excellent question. Okay. Okay. All right, well, this isn't exactly... So here's the definition of a vertical asymptote. The problem is that you, in previous classes, you didn't have limits to define vertical asymptotes. So that's why. So you're kind of, so then it becomes a bit wishy-washy. But this is what a vertical asymptote is. So f has a vertical asymptote. It's related to limits anyway. So vertical asymptote at x equals to a if either the limit as x approaches a from the left is equal to plus or minus infinity, or the limit as x approaches a from the right equals to plus or minus infinity. So that's it. So as long as, so it's a vertical asymptote as long as the limit from one direction goes to infinity or negative infinity. But that says absolutely nothing about the value of the function at that point. It could still be something, right? Because it doesn't preclude it from being some other value. Yeah.
So the asymptote would only apply in that piecewise function to the 1 divided by x portion of it.
Well, no, the function is a piecewise function, so it would be the the function. This function right here, this piecewise function that we defined, that function has a vertical asymptote at 0.
Okay. 2.
At x equals 0, right? But it does come from that part, the 1 over x part, which is maybe kind of what you're thinking.
So this would only appear in a piecewise function, not a rational function.
Yeah, it would have to be piecewise because you know the rational functions that you're used to don't have weird things like just random y values at vertical asymptotes. Yeah. All right. Hey, good questions, guys. Good questions.
One more question.
Oh, yes, go ahead.
In pre-calculus, we learned that you cannot cross vertical asymptote, and we can't have points on it. But now we learned that we can have one.
Well, you can't really, I mean, you can't cross a vertical asymptote really because, so think about it. So here, let me show you. Let me see. What would be, let me draw another picture. Okay, so, all right, so I'm just making this up. Let's say you have a vertical asymptote right here, right? That means that it has to go to infinity or minus infinity from at least one direction, right? So pick one. Right or left?
Left.
Left, okay. Infinity or minus infinity, which one? Minus infinity. Okay, so somehow or other it goes like that, right? Down like that. Now this line that is terribly drawn here, gets closer and closer to that vertical asymptote, right? Okay, now is it possible to cross? So like right here, this on this side, it could maybe have another vertical asymptote, right? Okay, but what precludes it from actually physically crossing over there? Right. As soon as you cross over the vertical asymptote, you don't pass the vertical line, and it's no longer a function. You can touch it, yes. So that's okay. So for example, it would be okay to have a function like this, for example. So you could have a function that goes like this, and then, bam, ends right there. That's okay, right? Because it's still a function. You could even have something like this, and then like that, maybe, right? Is that still a function?
Yes.
Sure, right?
Those are
That's
two
the
different
proof.
functions, right?
What is it?
Those are two different functions.
Well, the whole thing is a function, but it's a piecewise function. So in this case, it would be made up of 3 different functions, right? So it's the purple, and then the dot is one function, and then this other right side is another function.
Thank you.
Does that make sense? So yeah, things start getting a little bit weirder in calculus, as you've started to notice. But that's okay, that means that we're growing in our learning, getting smarter, hopefully. Okay, any other questions before we continue? Or
So you would never see say an arbitrary point on a rational function, as you were saying, because we were talking piecewise and rational. You might have a function defined piecewise, wherein a vertical asymptote, you would have a point that possibly is in the middle of the asymptote, however, would still be a function.
yeah.
Okay. Too far out.
Okay, so this DNE was for the one without it. So you can write down whatever you want. I guess since I already put DNE there, I'll take it off. But you can leave it how it was, and then it would be -5, right? Whichever one you want. Okay, now what about this limit from the left? What'd you guys say?
0.
What would it be? So the limit as x approaches 6,
Negative.
negative infinity, right? So that's from over here. So if I'm left of 6, I'm approaching 6 from the left. Where's the function going? It's going to negative infinity, right? So that's the vertical asymptote there. So here it's -infinity. What about approaching 6 from the right?
Positive.
Yep, it would be positive infinity, because now I'm looking at this side. And so what's this limit? Does not exist. Now, a small note. Hypothetically, let's say that, let's just say that it looked like that. What would you say the limit is? So what I did is I took the minus away. So it's not true for this function. But let's just say you approach from the left and the right, and it's equal to infinity from both directions. What would you say the limit is in that case? Yeah. That is what you want to say. So the correct answer is, so technically the limit does not exist because infinity is not a number, but you still would say infinity because it gives you more information. It tells you, oh, it's going in the positive direction, as opposed to when you just say it does not exist, it's like, that doesn't tell me anything. I don't know what does that kind of make sense?
Yeah. I was gonna say, so in your example, if you had two lines coming to the vertical asymptote approaching infinity, they would never cross. They would always.
Right, they wouldn't. So like a good example, a simple example of that is, say, here, this function. 1 over x squared, for example. So what does that look like? So it looks pretty similar to 1 over x on this side. But then what about left of 0?
Both on
It would be positive, right? Because you square negative numbers, so they're going to be positive. So it's actually identical. It's a mirror image here. So in this case, what would be the limit as x approaches 0 of this function? What would you say? You would say infinity, exactly, yeah. Because it's infinity from both directions. Does that make sense? Okie doke. All right. Good times. All right, and then what did you guys say for -5? What's this limit right here? The limit as x approaches -5 from the left. Nope. It's not -1. You can't tell. That's a good hint. That's good. Doesn't exist. Yeah, because you cannot. You can't be left of -5. The function is not defined for values of x less than -5. So there's no way to approach it from -5. Does that make sense? So you cannot actually approach it from this direction. So then it just does not exist.
So that's not passing -5, or you have the end of it. That is -5.
That is -5. Yeah, yeah.
I thought it was like going.
Oh, the intercept was -5, and then no. Yeah. So that the dot is supposed to be. So -5 is the endpoint.
But if it was past it, then it would be.
Then it would, yeah.
Okay.
Okay. So what did you guys say from the right? Yeah, -1, right? So if you approach -5 from the right, now you're over here, right? And it's approaching -1. So then what's this limit? The limit as x approaches -5. Does not exist. And what's f of -5? -1. Yep. Okay. Any questions for that? No? So far we've kind of seen, oh yeah, go ahead.
Why again is the limit as x approaches -5?
Which one's this one? Because
Yeah.
it doesn't exist from the left. Because remember, this has to be the same from both sides.
Say that if the function from the negative x existed at say -6x, then would a limit exist then at -5x? Or well, what I'm trying to say is if the dot was like shifted to the left or down to the left, then you would have a limit.
Yeah, so like, well, or even easier if, hypothetically, I guess if the function kept going, right? So like if it kept going this way for whatever reason, then you could approach it from the left, and it would be -1. Yeah. Yeah, it's just because the function ends there that you're not actually able to approach it. Does that make sense? Okay. So far we've kind of seen, the limit doesn't exist. Oh, let me ask you guys an easy question. Okay, easy question. Are you guys ready? Let me see. Let me find one here that maybe would work. What is that? Oh, okay. How about this? What's the limit as x approaches 5? What's f of 5? Okay. What's the limit as x approaches 5? 0, right? Is there anything to it there at that point? It's easy, right? That's why I said it was an easy question. But notice, so if the function is, if there's nothing going on, the function is just kind of smooth, then, so we notice we didn't really look at any points like that because it is obvious that the limit exists there, right? But sometimes it's easy to lose sight of the obvious. So we looked at basically the points where weird things happened. You know, there's like a jump, and then there's a vertical asymptote, and then all of a sudden there's a hole. But what about all the points in between those? At every single one of those, what would you say about the limit from both sides? It exists from both sides, right? And it equals, and you know, so like, I don't know, pick another one. I didn't put that many.
Before that, can you please show how you approach from the right and left?
Of which one?
5.
5? Right here? This one?
Yes. How you approach from right and left?
Well, it's from, so you want to kind of look at the x values to the left. So it's like, okay, so here's some x value left, and then you go to the function there. And so then you approach from the left like that, right?
Draw the little man.
And how
Oh,
right?
yeah. Okay. And then from the left, you're over here. So, I mean, the function keeps going down, right?
Right.
And it gets closer and closer to that vertical asymptote. So, you know, you kind of go this way up here, whatever, like that. And then, does that make sense?
Yes.
Any other questions? Can you guys think of any other kind of functions that are a bit weird where the limit wouldn't exist? What do you guys think?
The absolute value.
The absolute value. Okay, let's do this. Let me do. So we did that, right? Have you guys ever used Desmos?
Yes.
Yeah.
Desmos is pretty cool. Oh wait, didn't I show you guys Desmos last time? Or no? No? Desmos is pretty awesome. So Desmos is basically a calculator, but the cool thing about it is that it's really interactive. So like, so there's the absolute value function, right? So what's the limit of the absolute value function as x approaches a 0? So does the limit exist at 0? Okay, all right. No, stay. But anyways, I was going to show you guys, well, okay, let's do this. Back to the absolute value function. If you change any of these things, it'll change the graph right away. So like, for example, if I stick a 4 right here, it'll change it right away. If you do -3, for example, it'll shift it right away. And you can do sliders, which is pretty awesome. So like, for example, if I do A, it asks me, oh, do you want to add a slider? Sure, why not? How does changing that constant right there change the function? Well, that's how it changes it. That's pretty cool, right? Okay. Anyways, so we can kind of explore some things here. Can you guys think of any other functions before I come up with one?
What about the square root of, like, say, like x squared minus 4x plus 20?
Okay. Square root of x squared minus 4x plus 20. All right, what's the deal there? What's the limit of this function as x approaches any number? Do they all exist?
Yes.
They do. Why?
Because that's continuous.
Continuous? Okay. But what else? What else is interesting about? I mean, are square root functions always? Do they always look like that?
Yeah.
No, they don't. This isn't a normal square root function. If I graph square root of x, so it's right there, right? This one. What's the limit as x approaches 0 of square root of x? Does not exist, right? Why?
Because we cannot
Can't approach it from the left, right? Okay. So why is it that the other one doesn't have that?
Because its domain is all real numbers.
Yeah? Why?
You can approach it from both directions. And
Yeah, but why is it that the domain is all real numbers?
one-sided because of the square root.
Because what?
Because it should be positive on the square root. Then we have the graph on the both sides.
x squared minus, what did I write down? Now I'm looking, I'm like, oh, it looks different to you guys. Okay, now I see it. This sign right here, that's a plus. But anyways, well, that changes everything. But no, the reason why is because this is always, it's always positive, right? So if it's always positive, no matter what, then you get the square root and you always get a number, right? The reason why square root of x is not defined for negative numbers is because you can't find the square root of a negative number. But if it's always positive, well then, yeah, does that make sense? Okay. But let me show you guys some other weird things.
What about the greatest integer function?
Does it? I don't know how I would put that on Desmos. Floor? Maybe? There you go. Look at that. Okay. See, I knew Desmos wouldn't let me down. Alright, so this is the greatest integer function, or also called the floor function. So here, for example, so basically the greatest integer function, or the floor function, basically it's the greatest integer that is between the numbers, so like, but not including, well, greatest integer up to that number. So like, for example, what's the greatest integer of 0.5, let's say? It would be, you basically drop down, that's why it's called the floor. So you drop down to the lowest integer. So it's called the greatest integer, so it sounds a little bit weird, but so it's the greatest integer of 0.5 would be 0. What's the greatest integer of 0.9? 0. What's the greatest integer of 0.99999? 0. What's the greatest integer of 1.1? 1. 1.4? 1. Yeah. So what's the limit as x approaches 1 of the greatest integer function?
0.
Well, it depends.
Actually,
Switching from
it
left
exists.
to
It doesn't exist, right? Because it's different from both sides. So if I approach from the left, it's 0. If I approach from the right, 1. What about, okay, here, let me give you another one. What about, let me get my big white brush here. What about, let's see. What about, let's see. How about the limit as x approaches 1 of, all right, what's that? So imagine so think about it for a little bit. Think of the kinds of numbers. So like, for example, the limit as x approaches 1 from the left. So imagine numbers that are less than 1, right? You're getting closer and closer to 1. What is the greatest integer of those numbers? And then if you divide that by
1.
That'd be 0, right?
Yeah.
0
what do you
or
guys
1.
think?
0 and 1.
So of course we could graph it on Desmos, but then we learn nothing. So you guys have the right idea. So like, imagine, so what is it kind of that we're thinking of? We're like, if we write down numbers that we're thinking of, these are the kinds of numbers, right? These are numbers that are less than 1, but that are getting closer and closer to 1, right? So it's like if we're kind of thinking, what's the greatest integer of all of those numbers? No matter how close I get to 1 from the left, they're always going to equal 0, right? Does that make sense? So what you have, so this is kind of like you have all of these are going to be 0, this greatest integer, divided by these numbers that are getting closer and closer to the number 1, right? So 0 divided by any of those numbers, what is it? 0. It's always going to be 0, right? So this is going to be 0. What about from the right? So the same, if you kind of go through the same thought process.
1.4, 1.5.
Because if you have it, if it's the 4 of like 1.4, you'd be 1 divided by 1.4.
Yeah, but remember, it's kind of like it's a progression. So it's you want to make sure not to get stuck on, like, say, 1.4, 1.1, 1.01. It's like you're going from all the way and you're getting really, 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 really close to whatever the number is. So in this case, 1. So go ahead. I'll give you a minute to think about it. You can talk about it with your neighbor. See what you guys think. Talk it through with your neighbor. Don't be shy. Your buddy. Next door. I'll give you a minute. Yes.
Those
Yeah. Or the greatest integers.
Yes.
It's just gonna drop
Really
down.
complex.
Over.
No, I get the first
But
one.
then
You're saying,
it comes
let's
like
just pick one number,
they are
0.9.
very
So
complex.
that's 4 over 0.
For example, here it's 0.9.
Over 0.9. It's still equal to 1. So
Here is greater than
I think
here.
1.4 if you put
Then after
1.
complex, you become that. You're gonna be
So it'd be 1 over 1.4.
All right. So what did you guys come up with? What do you think?
That, the front.
1.
Isn't that simple?
It is just 1 because so you guys had the right thought process. I mean, basically what this is. So like what are the numbers you're thinking? Like 1.1, 1.0001, and so on and so forth. Kind of numbers like that, right? So what's the floor of every single one of those numbers? 1, right? Okay, so this is exactly the same as this. Identical to this. Do you guys agree? Because the numerator is always going to be equal to 1. Does that make sense? Always. No matter what. Because assuming you're close enough to 1, which you're getting closer to 1. So, I mean, don't, shoot off over to be like at 5.7. Well, that's silliness, right? Because you're approaching 1. But these two are basically the same thing, right? So, and then, so x is approaching 1, so then this is going to equal to 1, just like this is. Does that kind of make sense? Okay, so let's see if Desmos agrees with us. What does Desmos say?
What? Same thing.
Is that what we concluded? So from the left, we said it approached. So the limit as x approaches 1 from the left, we said it was 0. Which it is, right? That's what it is. And then the limit as x approaches 1 from the right, that's 1, right? It's a funny looking graph, right?
Yeah. Why is it so freaky after 1 or before 0?
Before,
Yeah, why does it go infinite?
well, I'll let you think about it. But think it through. So just like, no, but like, so what is it? So think of what is the floor? So if, let's say x is between -1 and 0. What's the floor of all of those numbers? -1, right? So it's like having, basically it's like having -1 over
increasing
x
the smaller number.
for that range, right? This interval right here. When you're looking at this interval, this is basically like having, well, what do I do this? Look at this. Look at this. Oh, bam. What do you notice? About minus 1 over x. It overlaps right there.
Yeah.
Right? And that's that section from minus 1 to 0. What about, for example, this one right here, this section? What would that be the same as? Negative 2 over x, right? For that little part right there. Does that make sense? And then minus 3 over x, 4. You can even make a slider. Look at this. And you can play it. Oh, where'd it go? Oh, it's not the same on the other ones. There you go. Pretty cool, right? Okay. Oh, good times. Okay. All right. So I wanted to show you guys some other cool stuff. Okay. That was pretty cool. And that was good that we talked about it because you guys have a homework assignment about the greatest integer function. So here's one that very common. So this is a little bit weird because so sine of x over x does that look right, that graph?
No.
Doesn't look right, right?
There should be a hole with one.
What's f of 0? What's the value of the function at 0? Yeah, it's not defined, right? Because you can't divide by 0. The other thing is, what do you typically have when the denominator 0, typically what do you have?
Asymptote.
Vertical asymptote. Not all the time, right? We saw last time you could have a hole. But that's kind of what's going on here, right? So like, so notice I hit here 0, it's undefined, but it won't graph it if I don't hit the button there. And so that's pretty interesting. So we'll talk more about that one when we get into limits. What about that? That looks pretty weird. So this is kind of strange because, well, it looks like they're playing pinball in there. So this is sine of pi over x. So what would you expect to have at 0? So when x equals 0, is it defined? It's not defined, right? Okay. Does that mean automatically that the limit doesn't exist? No, right? You have to go from the left, the right, see what's going on. So here, what happens as x gets closer to 0 from the right or the left?
It really starts freaking out. It's like
Starts going a little bit bananas, right? So like right here, so here everything's fine, no big deal, right? But then what happens as you get closer and closer?
Sounds like infinity. There's a couple too many ones.
Yeah, so what happens is it starts oscillating like crazy, and the closer you get to 0, the faster it starts oscillating. But why? Can anybody tell me why?
Because the period goes shorter. I think it keeps getting closer and closer to 0, but it's not.
Yeah, but what about the function makes it oscillate faster the closer x goes to 0? So just think of pi over x. What happens to, so if you just think of pi over x, what happens to pi over x as x gets closer to 0?
It gets
Larger. And it gets larger and larger and larger and larger Faster or slower?
Faster.
Faster, right? So if you're thinking, well, what does sine, the sine function do? It's just humming along, right, between -1 and 1 all the time, right? So, but what's happening is the inside is getting bigger and bigger, faster and faster and faster, which makes the graph oscillate between -1 and 1 faster the closer x gets to 0. Does that make sense? So here, you can zoom in, and if you have a calculator, you maybe, I don't know. How do you zoom in here? Oh wait, I know. You go over here, right? So like for example, if I do, let's get really close, like minus 0.01 to positive 0.01. And then I know that it's never going to go past 1, right? Does that,
Much more clear.
that's way better, right? Okay, well let's say I want to get closer even. So 0, 0, 1. So that's closer. That's even better, right? I can get an even better picture of what's going on, right? Oh, that's not good enough. Oh, I should get closer. Oh, then I'll really know what's going on here. Great, I did it. I've answered the question. And then I click through here, and you're like, oh, I don't know. What's happening? What's going on? So what would you say about the limit here? From either side. No, it's not 0. It doesn't exist. Because it just keeps oscillating. It doesn't actually go to 0. It just keeps going back and forth between -1 and 1, faster and faster and faster the closer you get to 0. This is just totally bonkers. It just doesn't exist. What is it? Yeah.
But based on graph, we say that the limit does not exist. How about if
Correct.
we want to solve it?
Algebraically?
Yeah.
Oh, well, that comes later. Yeah, we don't know how to do that yet. But we will, yeah, we will know. But we need to learn more. We need to learn more.
It'll just like oscillate into oblivion as it approaches the origin, but it'll never touch, I guess. Or-
Right, never. Just keeps oscillating faster. So the closer you think you're getting to figuring it out, the worse it gets. Because it oscillates even faster. And then it gets even worse and worse and worse.
Which you can do algebraically at some point.
Yes. Well, most of the time, yes. I probably would not call it simple, but there are techniques to make it easier a lot of the time. Okay. All right. Well, hey, good times, guys. Let's see here. Oh, wait. I should get my bucket. So any questions? So are we pretty comfortable with finding limits graphically? Yeah? Like looking at a graph, say, oh, find the limit at this value. Find the limit at this other value. Find the limit at this value. Just by looking at the graph, would you be able to tell? That's what we just did. Yeah, right? It's pretty straightforward once you kind of get around some of the kinks.